Hi, my name's Pete, and today I'll be talking to you about understanding chemical bonding and intermolecular forces and how that affects the property of substances, valence shell electron pair propulsion theory, or VESPR, and how this determines the shape of a molecule, and how to safely store chemicals in different states of matter. So there's three different types of chemical bonds: ionic bonds, covalent bonds, and metallic bonds. And it's worth noting that electronegativity is a measure of the tendency of an atom to attract a bonding pair of electrons. Firstly, we have covalent bonds, which are bonds between non-metals. So oxygens are not an example of a non-polar covalent bond. And that happens between atoms with the same or very similar electronegativities. Obviously, oxygens to O2 is two oxygen atoms, so they'll have the same electronegativity. And polar covalent bonds happen between atoms with different electronegativities. So we've got two different atoms, like hydrogen and oxygen in water. And also coordinate bonds happen in a oh, for fuck's sake. Hi, my name's Pete, and today I'll be talking to you about the different types of chemical bonding and intermolecular forces and how they can affect the substance. Hi, my name's Pete, and today I'll be talking to you about the different types of chemical bonding and intermolecular forces and how they can affect the properties of substance, valence shell electron pair repulsion theory, or VESPR, and how this determines the shape of molecules, and also how to safely store chemicals in their different states of matter. So there's three different types of chemical bonds: ionic bonds, covalent bonds, and metallic bonds. And also it's worth noting that electronegativity is a measure of the tendency of an atom to attract a bonding pair of electrons. So firstly, covalent bonds. There's different types of covalent bonds. They happen between non-metals. Non-covalent, non-polar covalent bonds like oxygen, O2, happen between atoms with the same or very similar electronegativities. Polar covalent bonds are between atoms with different electronegativities, like in water. And also coordinate bonds, like in ammonia, happens because it has three bonded pairs with nitrogen atoms and one unbonded pair. So the extra nitrogen atom borrows the unbonded pair to form a coordinate bond, which creates ammonium. And also we have ionic bonds, which happen between non-metals and metals, and they form when there's a high electronegative difference between the atoms, and as an electron is transferred from one atom to another to form positively and negatively charged ions. And finally we have metallic bonds, which happen between metals. They form when metal atoms lose their outer shell electrons to form positive ions, which leaves the valence electrons to move freely throughout the metallic lattice. Obviously the electrons are negatively charged and the metal ions are positively charged, so they attract. And different bonds can cause different physical properties. So diamond is different properties can include melting point, boiling point, electrical conductivity, solubility, and hardness, and they all dictate what applications that substance is used in. So firstly, we have diamond, which is formed from covalent bonds. It's a giant covalent structure. Diamond's extremely hard because it has a large amount of covalent bonds holding it together. And because it's so hard and has such a high melting point, it's used in industrial cutting and polishing tools. And sodium chloride, or table salt, is an ionic compound that forms a lattice structure. And ionic compounds are often soluble in water, so the sodium chloride dissolves into Na plus and Cl minus ions. Na plus is a vital part of many bodies' biological processes. It's needed for cell respiration and nerve function. And the Cl minus is an electrolyte and help regulates blood pressure. And copper is a metallic structure held together with metallic bonds. It forms a lattice of copper atoms with free-flowing delocalized electrons in between, which makes copper very conductive and malleable. So copper is perfect for electrical wires. We have VESPR. It predicts the geometry of molecules. VESPR models are based on the concept that electrons around a central atom will configure themselves to minimize repulsion. So beryllium chloride, it forms a linear structure because the two bonded pairs exert an equal amount of force against each other, so they move equal distance apart. And you see water has a bent structure because it has two unbonded pairs and two bonded pairs. The unbonded pairs exert more force than the bonded pairs, so it pushes the hydrogen atoms to one side. We've got tetrahedral structure like methane. It forms because it has four bonded pairs. Carbon has forms four bonds with hydrogen, and they all move an equal distance apart. Ammonium also has the same structure because it's an ion, so the nitrogen loses an electron and it ends up the same amount of electrons as carbon. We've got trigonal pyramidal, like ammonia, and that forms because it has three bonded pairs and one unbonded pair. So the unbonded pair pushes the three unbonded pairs slightly to one side. And we've got another ion which has the same shape because oxygen loses an electron to have the same amount as nitrogen. Okay, another type of forces that hold molecules together called van der Waals forces. They're not as strong as chemical bonds, but they do affect the melting and boiling point of a substance. So hydrogen bonds, which are similar to dipole-dipole forces, they happen between positively charged hydrogen atoms from one molecule and negatively charged atoms from another molecule. An example of this is water. Has quite a strong hydrogen force. Hydrogen bonding is the strongest, so water is held together quite well, which hydrogen bonds are what causes surface tension in water. So dipole-dipole forces are similar to hydrogen bonds. They're an electrostatic attraction between two polar molecules. So it's a bit like a magnet. It's the positive end of one molecule and the negative end of another, which attract together. And we have London dispersion forces, which are the weakest type of van der Waals forces. An example of this would be in graphite, where you have layers of carbon, and between each layer there's London dispersion forces, and it allows the layers of carbon to slide over each other, which is why graphite's used in pencils and also lubricants. Now we go into the correct ways of storing solids, liquids and gases. So solids are held together by strong intermolecular forces, and they should be stored in dry sealed containers to prevent contamination or reactions with air. And liquids should be stored in airtight containers to avoid evaporation. And gases, for example helium or nitrogen in that picture, should be held. They have really low boiling points, so they should be held in pressurised cylinders. And that also means you can store larger amounts, because when you pressurise a gas, it will turn into a liquid. So, in conclusion, you should know more about chemical bonds and how they affect physical properties, VESPA, different van der Waals forces, and how to safely store chemical samples. Okay, thank you for listening.